Hello everyone, and welcome back. Today we're going to be continuing our exploration of higher order differential equations and explore a very useful method for finding solutions to inhomogeneous differential equations. And this method doesn't only apply to constant coefficients differential equations, but more so if you have a function of x in front of your y double prime, your y triple prime, or what have you. This method can also help you in finding particular solutions to your differential equations. So as our sort of guiding example for this discussion, we're going to be taking a look at the differential equation y double prime minus y is equal to tangent of x. And you're like, well, that doesn't seem that scary compared to, the other ones that we've discussed, where we had constant coefficient and homogeneous equations. Because you're like, okay, well, I can solve the homogeneous differential equation because this is going to reduce to lambda squared minus 1. So we're going to have plus or minus 1 as our lambda values. So our homogeneous solution is just going to be equal to c1e to the positive x plus c2e to the minus x, right? So once you have your homogeneous equation, then you're going to be like, well, all I have to do is find a particular solution yp, and then I'm going to add up my yp and my yh, and that's going to give us our general solution. The only problem is this annoying little inhomogeneous term, because in our last discussion, what we pretty much did was do educated guesses. For example, if it's sine, we're like, okay, any linear combination of sines and cosines and their derivatives will also be equal to sine. If you have e to the x, any linear combination of its derivatives will also be itself. But when you get to like tangent of x, which as we already know is equal to a quotient of sine and cosine, and we know, for example, the derivative of tangent is secant squared. The integral of tangent also isn't the nicest of functions, but it's not too bad. It's just the natural log of cosine of x plus some arbitrary constant c. But if you do a second integral of tangent, in particular the integral of the natural log of the cosine of x, that's going to give us a nice little circus of fun. I invite you to try maybe on your own, but if you don't know special functions, I don't recommend you doing so. It's definitely going to give you a difficult time. So if you can't really guess a nice little function whose linear combinations of derivatives up to second order give you tangent, then that educated guessing method doesn't really apply here, right? But if it were some other functions that behave nicely under differentiation and iterative differentiation, then actually it's a little bit more easier to guess, which is where this next method, which is sometimes referred to as the variation of parameters, comes into play. So how the variation of parameters, which I'm just going to abbreviate by VOP, goes, is it looks at the homogeneous solution for our homogeneous part of our differential equation, and instead of using C1 and C2 as constants, what it does is it assumes that our particular solution is on the form u of x e to the x plus v of x e to the minus x for some functions u and v. Right? Because notice here that we have a product and or quotient of functions, right? We just don't know what u and v are, right? And generally speaking, for the general particular solution, that's just going to be equal to u of x y1 plus v of x y2, where y1 and y2 are independent solutions of our second order homogeneous differential equation. Okay, so let's see if we can build a little bit of theory for the general case, and then we'll return to our particular example, and then see if we can solve it with using these newly developed tools. Okay, so what I want to do is I want to consider our general second order differential equation y double prime plus a of x y prime plus b of x y is equal to our annoying, potentially annoying, inhomogeneous differential equation. And let's suppose that our homogeneous solution is c1y1 plus c2y2 with the Wronskian of y1 and y2, which, in case you don't remember, is the determinant of y1, y2, y1 prime, y2 prime, which is equal to y1, y2 prime minus y1 prime, y2. Let's assume that this is never equal to 0 for all x and their associated domains. Okay, i.e. y1 and y2 form an independent set, and hence that is truly our homogeneous differential equation solution. So variation of parameters works by letting our particular solution be of the form uy1 plus vy2, where u and v are some functions, right? And let's also assume um, with the additional requirements that u prime y1 plus v prime y2 will be equal to 0. Now, this is a little bonus thing because there's no real motivation as to why we would want this, but eventually what we're going to see is we're going to have an overdetermined system of equations with u and v in it. So in order to allow us to have a unique u and a unique v that are usually more practical to obtain, having this additional little requirement is going to help us out, right? But for the time being, let's just keep this in the back of our minds and we'll sort of introduce it when we need it. So this is going to be our particular solution to the differential equation. So let's plug in this into our differential equation by first finding the derivative of this yp function. So that's going to be equal to the first times the derivative of the second plus the second times the derivative of the first, and then we're going to have the first times the derivative of the second plus the second times the derivative of the first, right? So that's just the product rule 2 times on the first yp function. Okay, now keep in mind we have assumed that u prime y1 plus v prime y2 is equal to 0. So if we sort of take a look at what we have here, we have our u prime y1 and plus our v prime y2. That's just going to be equal to 0. So we're just going to be left with u1 prime plus v y2 prime. So that's going to be our yp single prime. Okay, and if you do not implement this little requirement, you're going to have the full thing, which is going to make the next statement extremely ugly, which is where that motivation sort of comes into the picture. So our yp double prime is going to be equal to the derivative of yp prime. So it's going to be equal to u prime y1 prime plus u y1 double plus v prime y2 prime plus v y2 double. Right? So that is the second derivative of our particular solution. We have our first derivative of our particular solution. Now we're just going to plug this, and that original yp into our original inhomogeneous differential equation and see if we can come up with anything magical. All right, so our y double prime, as we've already proven, is going to be equal to u prime y1 prime plus u y1 double plus v prime y2 prime plus v y2 double. So that is our y double prime. And then we're going to have our a of x times our y prime, which is going to be equal to u y1 prime plus v y2 prime, right? So that's our y prime term. And then we're going to have our next term, bx times y, which is uy1 plus vy2, and that's going to be equal to our f of x. Right? So y double prime plus axy plus by equals 0, where a and b are allowed to be any functions of x, need not be constant coefficient. So what I want to do is I want to group all of the things that have u in front of them, just u. So we're going to have a u y1 double prime there. We have a u y1 prime there, and don't forget your little a. And then we're going to have our u1 y1 in front of there. So once we rearrange, we're going to have u times y1 double prime plus a y1 prime plus b y1 there. And then I'm going to look at my v terms. So where's my v? So v y2 prime, double prime I mean, and v y2 double prime, don't forget your a. And then we're going to have our v y2 there, don't forget your b. So that's going to give us plus v y2 double prime plus a y2 prime plus b y2. And then we're going to be left with everything else. So we're going to be left with this u prime y1 prime, and where's the last thing? So v prime y2 prime, and everything else is accounted for. And don't forget your little fx on the right hand side. So we're going to be left with plus u prime y1 prime plus v prime y2 prime, and that's all going to be equal to f of x. Now keep in mind that our y1 and our y2 were particular solutions to the homogeneous differential equation. So that means this must be equal to 0 and this must be equal to 0 regardless of what u and v are equal to. So this part and this part just eliminates, which is just going to leave us with this little baby ordinary differential equation on the right hand side, which is actually very beautiful, at least in my opinion. So we're going to have u prime y1 prime plus v prime y2 prime is equal to f of x. We already know what y1 is. We already know what y2 is. We just do not know what our u and v are, right? So we have this equation here, in particular u prime y1 prime plus v prime y2 prime is equal to f of x, and we also have that other requirement from before on u and v, in particular u prime y1 plus v prime y2 was equal to 0. So that's the other requirement that we required. So what we have here is a system of differential equations in terms of u prime and v prime. So that's going to be our unknown derivatives of our functions, and then we can integrate and find those particular solutions. So when we write this as a matrix, we're going to have y1, y1 prime, y2, y2 prime. That matrix should look familiar. And then we're going to have our u prime and our v prime hanging out in our unknown vector. And then we're going to have this particular differential equation. So isn't that very, very nice? Okay, so we're going to call A to be equal to our y1, y2, y1 prime, and y2 prime, which is going to give us the Wronskian of our solutions, y1 and y2. So keep in mind, w of y1, y2 is just going to be equal to the determinant of A, which is just going to be y1, y2 prime minus y1 prime, y2. And keep in mind, this is never equal to 0 by assumption, implying independence. So once we solve this equation, A u vector is equal to B vector matrix equation. So A u is equal to B. We can just apply the inverse of this little 2 by 2 matrix to both sides, and then we have our solution. So our inverse matrix A is going to be equal to 1 divided by the Wronskian of that expression. And then we're going to be like, okay, well, what's that going to be? So we're just going to be reversing these elements and negating the other two. So we're going to have y2 prime y1 minus y2 minus y1 prime. So that's going to be the inverse of that particular matrix A. And then we can solve this equation for u prime v prime. So that means u prime v prime will be equal to 1 over the Wronskian times y2 prime minus y2 minus y1 prime y1 times that vector on the right hand side, which is 0f. So once we multiply that, we're going to have 1 over Wronskian times, and then we're going to be multiplying those vectors by each other. And keep in mind, this is going to be a 2 by 2 matrix. Right? So when we multiply a 2 by 2 by 2 by 1, we're also going to get a 2 by 1 vector, which is going to be equal to 0 times y2 prime minus y2 times f for the first element, and then 0 times minus y1 prime, and then plus y1 times f for our second element. And once we reduce, we're going to have 1 over the Wronskian times minus fy2 and fy1 as our first and second components of that vector. So that is what u prime v prime is equal to. So if two vectors are equal to each other, that means their elements are equal to each other. So we can solve this vector equation for their components. So we're going to have these very important equations. U prime of x is equal to minus fy2 over the Wronskian, and v prime x is equal to fy1 over the Wronskian. And we don't want u prime and v prime, we just want u and v. So we're just going to be integrating both sides of those equations with respect to x, since this is a separable equation. And then we have our goal equations. So u of x is going to be equal to the negative integral of f of x, y2 of x over the Wronskian of x dx, plus some constant c1, but we're going to be merging that into the other constants as well if we really need to, so we need not write it here. And then our other Vx is just going to be equal to the integral of f of x y1 of x over the Wronskian of x dx. So this is going to allow us to get our particular solution to our inhomogeneous equation. As long as we can take the integral of these, then we shouldn't have that much worries to deal with. So now that we have some of the theory built for the variation of parameters, now let's go back to our original equation that sort of motivated this investigation. So we have our y double prime minus y is equal to tangent of x, and we already know the homogeneous solution to this differential equation. It's just a linear combination of e to the x, e to the minus x, and we've already verified in the past that if e to the ax and e to the bx is our proposed solutions, that actually forms an independent set as long as a and b are not equal to each other. So what I'm going to do is I'm going to name y1 and y2 so we don't get confused. So y1 I'm going to let e to the x be, and y2 be equal to e to the minus x. So the Wronskian for this particular set of solutions is going to be equal to e to the x, e to the minus x, and their derivatives, which is e to the x and minus e to the minus x. And the determinant of that is going to give us the Wronskian. So that's going to be equal to minus e to the x times e to the minus x is just going to be equal to minus 1. And then minus e to the x times e to the minus x, that's also going to be equal to 1. So that's going to be equal to minus 2, which as far as we know is never going to be equal to 0 for all x in the set of complex, right? So the Wronskian is equal to quite a nice little number, which is actually pretty nice. So now we need our particular solution, yp, which is going to be equal to uex plus ve minus x for some functions u and v. So what are those functions u and v? Well, we've already proven that u of x will be equal to the negative integral of our f of x function, which is equal to the tangent of x, times our other function associated to e to the minus x, right? So u has y2 in it and v has y1 in it, so they're sort of reversed from each other, and that's going to be divided by our Wronskian, which in this case is equal to minus 2. So that's going to give us that first term. So once we sort of clean this up just a little bit, we're going to have that u of x is equal to the half integral of tangent of x times e to the minus x dx. So that's actually going to be our u. It's actually quite a nice integral to look at. And our v is going to be equal to the positive integral of our f of x function times y1, which we've defined to be equal to e to the x, all divided by our Wronskian, which is going to be minus 2. And once we clean that up a bit, that's just going to be equal to minus 1/2 times the integral of the tangent of x e to the positive x dx. And that's going to be our v. And you might be wondering, well, aren't you going to do those integrals out? Indeed, I will not, because if you know anything about non-elementary functions, you probably know that tangent times e to the minus x is a non-elementary function. So I would define that to literally be a function called v or a function called u, but nonetheless, that gives you your particular functions, right? So what will be the general solution to our original differential equation? That would just be equal to c1 e to the x plus c2 e to the minus x plus u1 times e to the x plus, well, not u1, but rather u of x, which is this little nasty integral that I have defined here. And my pen doesn't seem to want to work, and that's okay. And then we're going to have v times e to the minus x. And we can also factor out that e to the x and e to the minus x if we really want to, and write this instead as our general solution is equal to, we can do e of x times c1 plus our u of x function, and then plus e to the minus x times our v of x function, right? And then you can sort of see why I didn't want to write our constants at the end of these little integrals, right? Because you could be like, oh, that's plus c1, that's plus c2. They're actually going to sort of blend in with these particular constants, so you need not define them here. But that would be the general solution to our original differential equation, provided that you can express and analyze these special functions as they are written here. The next differential equation that I want to sort of explore is a second order differential equation that's linear, but also non-constant coefficient, but let's just make it homogeneous just to make things a little bit easier, right? So the non-constant coefficient portion is that, we have x squared in front of our y double prime, we have our x in front of our y prime, we have a quadratic function in front of our y. It is homogeneous, so that's actually, the least of our worries. So then it's like, okay, well, how can we solve this? So one's eventually going to be able to realize that you're not going to be able to have one method that sort of fits all differential equations, because obviously if you can solve all these, I can throw in some nonlinear terms, which sort of echoes the same exact issue we had once we were talking about first order differential equations, which we eventually realized, well, if we can find an integrating factor and turn it into an exact differential equation, we can actually always solve it. It's just finding that integrating factor, which is always a big mystery. Right. But if you are able to sort of, look at the slope field and identify one solution that actually works, sometimes you can actually construct the rest of the solution just from that observational solution that you've sort of figured out from the slope field, for example. So if one were to look at the slope field, one may conjecture that a solution to this differential equation is the sine of x over the square root of x. So one can ask, well, is this truly a solution to the differential equation, yes or no? And you should be able to verify it. So let's actually go through a little bit of algebra to sort of see how one would do that, because this function isn't exactly super trivial to deal with, right? So the first derivative of this function via the quotient rule is just going to be 2x times the cosine of x function minus the sine of x function all over 2x to the power of 3 over 2. I recommend keeping things in fractional exponent form. It's going to be a lot easier to deal with later on. And the next thing I want to do is, find the second derivative of that particular function. And once simplified, you're going to have 3 minus 4x squared times the sine of x. And then we're going to have minus 4x times the cosine of x all over 4x to the power of 5 over 2. Once you have your y prime, y double prime, and your y, we're just going to be substituting them into our original differential equation and just making sure that that does indeed work. So once we do so, and we're like, okay, well, what is x squared y1 double prime plus x y1 prime? And we can work with the last term just in a moment. What will that be equal to? So that's going to be equal to 3 minus 4x squared times the sine of x minus 4x times the cosine of x. And we're going to be multiplying this by x squared. So keep in mind, x squared is the same as x to the 4 over 2. So the 4 over 2 and the 5 over 2 are going to cancel, just leaving you with a 4x to the 1 out of 2 on the bottom. And similarly for the x times y1 prime, because keep in mind x is the same thing as x to the 2 over 2, so the 2 over 2 and the 3 over 2 are going to cancel. So we're going to be left with 2x times the cosine of x minus the sine of x all over 2 times x to the positive 1 over 2. And you're like, okay, well, I need a common denominator, so let's just multiply this top and bottom by 2, and that's going to give us a common denominator of 4 square roots of x. So once we have that, we're going to have, what are we going to have? So let's just distribute this out. So we're going to have 3 sines of x minus 4x squared sines of x minus 4x cosines of x. And then over top here, we're going to have 4x cosines of x and then minus 2 sines of x all over 4 square roots of x. And then if you sort of look at what we have here, notice that we have a minus 4x cosine of x, a positive 4x cosine of x. So those are going to sort of cancel each other out. We have a 3 sine x minus 2 sine x. That's going to give us a 1 sine of x. And then that 4x squared sine x term that's sort of chilling out by its own. So this is just going to be leaving us with the sine of x minus 4x squared times the sine of x. So both have a sine. That's pretty nice. And then we're going to have 4 squared of x on the bottom. And then we're going to be left with 1 minus 4x squared over 4 times the sine of x over the square root of x. I can divide that 4 into each of these terms partially, and I'm going to have 1/4 minus x squared times the sine of x over the square root of x. And if we sort of go back to our original differential equation and what we sort of had given to us, notice that we have x squared minus 1 over 4y, and we have 1/4 minus x squared, which is just the complete opposite of it, right? So since that's the opposite of the last term that we have, that means they're going to cancel out with each other, which means that y1 is equal to the sine of x over the square root of x is a solution to our quite difficult looking ODE, right? And that should make you happy. And you're like, well, okay, well, if we have one solution, we have a second order differential equation, it's homogeneous, therefore all we need is just one more, and I probably don't want to sit here and start guessing. Maybe cosine of x over square root of x would be a good one to guess. But is it possible to construct the second one from the first? And the answer is, of course, yes, because we know that this function and the other one has to be independent of each other. So using that little bit of information, we can actually use the Wronskian to our advantage and these integrating factors to sort of reconstruct. So let's just state a theorem that we're not going to prove here, but it's actually not quite hard if you use the Wronskian as a guiding tool. So if axy double prime plus bxy single prime plus cx of y is equal to 0, and let's assume that y1 is a particular solution to this differential equation, then the second solution, y2, is actually going to be equal to y1 times the integral of e to the minus integral power of b over a times dx all over y1 squared dx is the other solution. And in particular, it's the other independent solution, right? And again, the Wronskian is definitely going to be your friend here when trying to prove this if you're interested in that. Right, so we've already given that our y1 for our particular function or differential equation is sine of x over the square root of x. And let's just recall what our differential equation was. Our differential equation was x squared y double prime plus xy prime plus x squared minus 1 over 4th times y, and that's going to be equal to 0, right? And let's just wait until my pen decides to write. So that's going to give us our differential equation. Now notice that in this form that's going to construct our second solution, it actually doesn't really care about what c is, which is actually pretty nice, right? So there's our a and there's our b, so that means b over a is going to be equal to x over x squared, which is just going to be equal to 1 over x. And if we do the minus integral of 1 over x dx, that's just going to be equal to x to the minus 1. Right, so once we have that, that's actually pretty nice once we that particular thing out. So we're just going to be left with 1 over x as our top of our second integrand for our second solution construction. So y2 is going to be equal to y1. So y1 times the integral of e to that thing, which we've already verified to be 1 over x, all over y1 squared. So y1 squared is going to be what? So that's going to be equal to sine squared of x all over x. And notice that these x's cancel, so that's actually a very nice thing. And then we're just going to be left with 1 over sine squared, which we know is going to be equal to cosecant squared of x. Right? So we're just left with cosecant squared of x dx. So we should remember from single variable calculus that the integral of cosecant is negative cotangent squared. So we're going to be left with sine of x over the square root of x times negative cotangent of x plus c, I guess you could say. But we're going to mix our constants in a little bit later. But let's just throw it in just for sake of simplicity. And then we're like, okay, well, what exactly is this particular thing? So remember that cosine over sine is equal to cotangent, and the sine and sine are going to sort of cancel each other out. So what you're left with is just minus cosine of x over the square root of x plus c times that sine of x over the square root of x function. Right? So if that is your y2, notice that it's very related to our y1, and we shouldn't be surprised of that because, sine and cosines usually come in pairs. So from this, we can see that our general solution, yg, is just going to be equal to c1 times the sine of x over the square root of x from our first verification, and we can also combine this c with that other c to form our c1, and then we're also going to have our c2 times the cosine of x over the square root of x, where our minus sign is sort of inflated inside of that c2. And that gives us our general solution to the original differential equation. So we see that the method of variation of parameters can be very, very useful in finding integrating factors or general solutions to inhomogeneous equations, and also finding other solutions if we already have our first. So, in the next video, we will continue our exploration of higher order differential equations and look at some other tricks that can be used for solving them. Hope you enjoyed this video, and I'll see you there. Take care.